In the first and second parts of this video lecture, we have seen the definition of how we integrate, what it means to integrate an extended BOREL function on a subset of the sample space. We have seen the fundamental theorem of calculus, which in practice is many times how we actually compute an integral. We have expanded this diagram and shown that now when we have a BOREL function defined on the target sample space, then we can define a pullback of that function. And we saw the change of variable formula, proved it only for one particular case, the case when the function is a binary type of function. And we've seen that we can either integrate a function defined on the target space with respect to the push forward of a measure. You give us the same value as integrating with respect to the original measure on the source space, the pullback of that BOREL function or extended BOREL function. And now in this part of the lecture we'll discuss things that happen almost everywhere or almost surely. So almost in measure theory and probability theory means something that holds except on a set of measure zero. So when we say that two things, one thing happens almost everywhere, it means there exists some set A whose measure is zero, such that this property holds for every omega which is not in A. So it's not really everywhere, there's an exceptional, we accept that the existence of an exceptional set of points where this property fails to hold. When we say almost every omega, it means every omega except those in a small set. If we are on a probability space and we say that some event occurs almost surely, that means the event occurs with probability 1, which means the probability of that event equals 1. And when we say that some property holds almost surely on omega, that means it holds for almost every omega, which means for every omega inside a certain event that has probability 1. It is to be remarked that all these expressions here, they depend, and we do not make that dependence explicitly, they depend on a certain measure. We choose a measure, and for different measures, different things will hold almost everywhere for almost every omega, etc., etc., etc. If it is not clear in the context, or we want to make sure it will be clear in the context, we can add a mu here. We can say it holds mu almost everywhere, or some property holds for mu almost every omega. We can say some event occurs P almost surely, and we can say that some property holds true, again, P almost surely on omega. So we can add this prefix P or mu to specify explicitly the measure being considered. And since measure theory is a very robust theory, it's very insensitive to what happens in sets that have measure zero. And for most purposes in this module, and for most purposes when integration is happening, it really does not matter what happens in sets of measure zero. So if two functions f and g are equal mu almost everywhere, what does it mean? It means, well, the set of points omega where f is different from g, that set has measure 0. This is what it means for two functions to be equal almost everywhere. So it's everywhere except, and here's the except, on a set of measure 0. And what this proposition is saying is that integrals really don't care about the difference between two functions that are equal mu almost everywhere. And to make this precise, what it says is if f equal g, if two functions are equal mu almost everywhere, then their integrals are equal provided one of the two is defined. So unless they are both undefined, they will, one of them will be defined, and that will imply that the other one is also defined and takes exactly the same value. Let's see how we can prove this proposition. Start defining the set A, which is the set where the functions may disagree, and by assumption the measure of the set A equals 0 because the functions are equal almost everywhere. Then let us define these two extreme functions, age plus and age minus. Let's define them as follows. They will be defined to be f of omega, which is the same as g of omega, if omega does not belong to A. So if omega does not belong to A, then f of omega and g of omega are the same, so we can choose whichever one. They are the same. To define age of omega, both age plus and age minus of omega, they will agree. And then we can now define this function to be plus infinity when omega is in A. That will be age plus, and age minus will be defined as minus infinity. And why do we do that? Well, because now we have age minus is a lower bound for both for f, and age plus is an upper bound for f. And they're also upper bound and lower bound for g. And now, to conclude, we just need to note that the integral of age plus, age minus, has to be equal to the integral of age plus, and to show that, it is enough to show that, well, we can define also some age 0 that will take values 0 here when omega is in A, and we just need to note that, well, age plus or minus are both equal to age 0 plus or minus infinity times the indicator of A. And this function here is a function which takes values infinite or 0 or minus infinite, so we know exactly what its integral is. We can compute its integral from the very basic properties of integrals, and its integral will be 0 because the measure of A is 0. So this is 0, so just by linearity then of the integral of age plus and minus will coincide with the integral of age 0 if it is defined. If it is not defined, then we can bound from above and from below the positive and negative parts of these functions and show that none of them is defined. Let's omit the details. I think this shows very well the idea of the proof. A complete proof following exactly this idea, but splitting this auxiliary function in a more precise way, can be found in the lecture notes. And this will conclude this video lecture.